So first moment, the expectation of a random variable. Try to use it. Here's an exercise. Try to use it to show that, use first moment, that the simple fact that for every graph G, there exists a bipartite subgraph of it, retaining at least half of the edges, with E of G prime is at least E of G divided by 2. Okay, that's first exercise. Second exercise is some classical result, actually. To prove that a lower bound on the diagonal Ramsey number. So lower bound on diagonal Ramsey, KTT, KT. Okay. Prove that it's at least some 1 over E, 1 plus little o1, t times 2 to the t over 2, some exponential lower bound. So for the second exercise, I want to say a few words. How the simple way of applying first moment is that, so the one way of applying first moment is, suppose we want to show with high probability tending to 1, some good events happens, okay? Then to do this, we can define X as the random variable counting the number of bad configurations. All right. So let me say this good event is A. Then the A occurs such that A occurs if and only if there's no bad configuration. So example, let's look at this one here. If you consider this exercise above in the Ramsey, let's consider a random 2 coloring. And the event, what is the event A? If you want the lower bound, that means you want the coloring with no monochromatic KT. So the event is no monochromatic KT, right? And what will be the bad configuration here? The bad configuration is the number of monochromatic KT. So when the number of monochromatic KT is 0, of course, event A occurs. This is the number of monochromatic KT. So, okay. Now, if we can show that the expectation of X is less than 1, then by the previous proposition, we know that there exists an outcome of X, exists a coloring, random coloring, one of the outcome, such that X is at most this expectation, less than 1. But X is integer valued, right? When it's strictly smaller than 1 and are negative, that means it must be 0. this implies x is 0. So there exists an outcome of the coloring, sorry. There exists a two-coloring outcome of the random event, which is a two-coloring of edges. Such that x equal to 0, meaning that A occurs. So this is one way to prove a lower bound here. One can do slightly better by so-called alteration. So here's a trick. This is the alteration to improve. What is alteration? Alteration means, let's say you are coloring Kn, right? Then maybe the expectation is larger than 1. But we can, by delete one vertex from each monochromatic KT, we will leave with m minus x vertices with no monochromatic KT, right? So you just need to, the remaining graph, the remaining induced complete graph, the coloring there is a nice coloring that we want. So again, that means this means, so there is a good coloring, two coloring on at least m minus the expectation of x many vertices. Okay? Because there exists a x that's at most expectation of x. So, right? So m minus x is at least this. Any question? So, another way of applying first moment is to use Markov to prove one side of a threshold phenomenon in random graphs. So let me first briefly recall a random graph, Erdős-Rényi random graph. This is a probability space of graphs. So m vertex graphs, where every pair of vertices is connected with probability p. Okay. Independent of others. Okay. So in this model of random graph, we can define for a property P. So for a property P, we can define the threshold function. The threshold function of a property P So this is, let's say, this threshold function is Fn. It satisfies the following. You need to satisfy two things. One, when p is much smaller than this threshold function, then with high probability, or almost surely with high probability, GMP does not satisfy this property P with high probability, or almost surely. It's the same. Almost surely. This almost surely means this. Just means with high probability. Okay. But if P is much larger than f of n, then with high probability, almost surely, it does satisfy the probability P. So to prove a function is a threshold function for some property P, we need to do two things. Below the threshold, with probability tending to 1, the random graph would not have property P. Above the threshold, with probability tending to 1, GMP, the random graph, will satisfy the property P. So let's first see an example. Let's first see the Markov. We can use the first moment Markov often to prove the first part of the threshold function. Okay, so we can use Markov inequality to establish this first part. Okay, and there's a second part here. So how do we do that? Well, okay. So let's do it through an example. So the example is the property of containing a triangle. Let's consider an example. Consider the property which is containing a triangle. Well, in other words, the clique number is at least 3, right? It's the same. Okay. So we claim that the theorem is for this property. Maybe let me just write like this: P triangle. It's the property of containing triangle as a subgraph. So for this property, the threshold function for this property, we will see that it's 1 over n. We will prove the first part. First part means we need to show when P is much less than 1 over n, then with high probability, that means what? That means with P, the probability that GMP contains a triangle tending to 0, right? With high probability does not satisfy P, meaning that there's no triangle. So let's define x to be the random variable counting the number of triangles. This is a random variable. What is this event then? So this event becomes that we want to prove GMP contains a triangle is the same as the probability that x is at least 1. Right? There exists a triangle. We want to show this goes to 0. This is the same as showing that so our new goal is to show that x equal to 0 probability tends to 1. The complement of this event is this event. It's again, x is a non-negative integer valued random variable. So it's the same. This is the new goal. All right. Well, this is not very. This is the new goal. And this is where Markov kicks in. So how can we use Markov? Let's recall. Any questions so far? Markov says for a non-negative random variable, the probability that x is bigger than 1 . Oh, wait a second. Do I need to write? I don't need to write this. Sorry. I don't need to rewrite it. We can directly use Markov. Okay. So this is our goal. We want to prove that the probability that x, the number of triangles in GMP, is at least 1 goes to 0. How do we do that? Well, by Markov. This is at most the expectation of x divided by 1, right? The probability that x is at least t is at most ex over t, which is the expectation of x. So that means we just need to show enough to show. Suffice to show this. Expectation goes to 0. So, right? This is the new goal. Expectation goes to 0. If the expectation goes to 0, probability that x at least 1 goes to 0. And that's what we want. Now, expectation is easy to compute. This is the, let's do it slowly. That's the sum over all x, let's say a, where a is a set of 3 vertices. You range over all 3 set of vertices, 3 vertices sets. And xa is the indicator function that this is the indicator function for a inducing a triangle. Okay. By linearity of expectation, this equals to, this equals to linearity of expectation, sum over all a, expected value of xa. Okay. The number of a is n choose 3. This is the probability of a, which is this equals to the probability that xa is 1, which equals to p to the 3. The 3 sets has 3 pairs. All edges needs to be there. That's when it's inducing a triangle. And all 3 pair of edges inducing an edge independent of others. This is how we define Erdős-Rényi model. So we have these. This is roughly n cube p cube over 6. But what do we know? We know what we need to show is when p is much less than 1 over n. When p is much less than 1 over n, this goes to 0. That's what we want. So this is an example of how to use Markov to prove the one side of the threshold phenomenon. How do we prove the other side? To prove the other side, okay, let me see the order of things I want to explain. Right. To prove the other side, what do we need to show? When p is much larger than 1 over n, then with probability tending to 1, you satisfy p, that means there is a triangle. X is at least 1. So let's write it here. To show 2, i.e., when p is much larger than n, the probability we have the probability that the number of triangles is strictly bigger than 0. This is strictly bigger than 0, right? X is non-negative integer value. This goes to 1 with high probability. There is a triangle. You satisfy property P. Good. So in the first part, we show that if expectation tends to 0, then the probability that X is positive is going to 0. But here, when P is much larger than, so when P is much larger than 1 over n, we have the expectation of X. Remember, this is n cube p cube over 6 tending to infinity. So we have a random variable counting the number of triangles tending to infinity. And can we say that the probability that this random variable is positive, a non-negative random variable, expectation tends to infinity? Unfortunately, this is not enough to claim that the probability that X is positive tends to 1. So, but however, expectation tending to infinity is not sufficient to imply. To be precise, maybe let me for a non-negative, maybe I don't need it. It's okay. It's not sufficient to imply that the probability X bigger than 0 tends to 1. Why is that the case? For example, consider, let's say we have some lottery events, lottery for New Year. You are in the company of, so in a school, okay? Consider a school of, let's say, 100 students. And one of them is you, okay? Then we're gonna randomly pick a student and give a prize of, let's say, a million yuan. Okay. Now let's let X to be the random variable. That's the prize money obtained let's say a student, let's, how do I say? Let's give including you. Okay. So this among 100 students, one of them is you. Then X is the random variable that the prize money that you get. You will get. Let's compute the expectation of X. The expected value of the prize money that you will get, well, with probability, we choose among 100 students uniformly random 1 student. So the probability that you are chosen is 1 over 100. So with 1% probability, you'll get picked. And the money that we get is 1 million yuan. Plus, the remaining is 0. If you don't get picked, you don't get anything. So this expectation is what? Is 10,000 yuan. Okay, this is the expectation. But what is the probability? And I can modify this prize money so that this guy goes to infinity, can be arbitrarily large. But the probability that X, the amount of money that you get, is positive. Positive means you must get picked. It's 1%. Of course, it does not go to 1. It actually can be arbitrarily small. This can be arbitrarily small, right? Does it make sense? The problem here in this example is that in this bad example, so there's a, however, there's this twist here. The problem here is that the variance is too large. Okay, so the problem here in this example is that the variance is too large. So in other words, if we can control the variance, then these kind of bad events will not happen. Now we are moving to the second part of the probabilistic method, the second moment. This is where we're going to use variance to control how a random variable spread around its expectation. All right. So we will show that when the variance is not too large, then when expectation goes to infinity, we do have this. Any question for this example? So let's first recall. Now we are stepping into the second moment. Second moment means E expectation of X squared. But we're going to look at this another one, a more common one, which is the variance of a random variable. So the variance of a random variable, let's recall from undergraduate probability. This is the expectation. This is the variance of a random variable. X is the expected value of the squared deviation from its expectation, from its mean, i.e., we would denote it by VAR, variance of X, is the expected value of the deviation from its mean squared. Okay. And it's easy to show that this is the same as expectation of the second moment, expectation of x squared minus expectation of x squared. All right. We're going to define also its standard. This is the variance. We can define standard deviation to be the square root of the variance. We will denote it by sigma of x. It's the variance of x. You take the positive square root. Okay. So basically both variance and standard deviation, what they do, they measures how spread out a random variable is from its expectation. Okay. What it means is that if the variance or standard deviation is small, that means more concentrated around its mean. Let me use mu for the mean of a random variable. And if the variance is large, then it's more spread out, not concentrated around the mean. So now let's see the very important inequality involving second moment, the Chebyshev's inequality. Chebyshev's inequality which measures the probability that a random variable deviates away from its mean. This is the probability. So for any random variable x, and for any k, which is a positive real number, then the probability that x deviates away from its mean, mu, I will use mu for the expectation of x. Okay. So the probability that x deviates away from its expectation by more than k times the standard deviation is at most 1 over k squared. This is Chebyshev's inequality. Okay. Let's prove it. The proof is simple. We can derive it from Markov using first moment. So how do we derive from Markov? So the idea is we can apply Markov to this, to the squared deviation from its mean. Okay, proof. Let's look at these events. The probability that x minus mu deviates away by k times the standard deviation is the same as, let's write it, let's square both sides, is the same as x minus mu squared is more than k squared sigma squared. Okay? Now we can use Markov for this random variable. By Markov, this is at most Markov expectation of this random variable. And notice the expectation of squared deviation is just nothing but the variance divided by this amount of deviation, which is k squared sigma squared. Okay. Oh, I forgot to say, I write sigma to be the standard deviation of X. Okay. And this is just variance of X, which is sigma squared. So you have 1 over K squared. Easy. Very good. Now, let's first, okay. Let's first see what Markov implies. To get some feeling. So if you recall this, so in particular, it follows from Markov, Chebyshev, that for any random variable with at least 3/4, 75% of the values is within 2 times the standard deviation. So if you take k equals to 2, we get that the probability x minus mu more than 2 times standard deviation is at most 1 over 4. This means, so at least 75, 3/4 probability, 75 of the values of x are within 2 times the standard deviation of mean, right? And similarly, at least 88% are within 3 times standard deviation of mean. If you take k equal to 3. If you take k equal to 10, so with very high probability, 99%, you are within 10 times standard deviation of mean. Okay. How do we use this? We can now use it to prove the other side of this threshold thing. So recall what we need to prove. The threshold thing is that when p is larger than the threshold function, we need to show that with high probability tending to 1, GMP contains a triangle, meaning this random variable x counting the number of triangles is strictly bigger than 0. Okay. So before that, let's recall some basic fact about, because this x counting the number of triangles will be the sum of some indicator function xa, where a is a triple of vertices, right? So if, let's do some calculation, if x is the sum of some random variable xi, I goes from 1 to m, let's say, then its variation of x is the same as, easy to check that this is the sum of the variance of each xi. I goes from 1 to n, m. Okay, plus for different distinct ij, the covariance of xi, xj, where the covariance of xi, xj is the covariance of 2 random variable, ab or xy, is the expectation of xy minus expectation of x times expectation of y. This equals to 0 if x, y are independent. Okay, good. Now, let's prove the other side. So proof of 2, i.e., we need to show that when P is much larger than 1 over n, then with high probability, GMP contains a triangle. In other words, the probability that X, which is the number of triangles in GMP, bigger than 0, tends to 1. Okay. We're going to prove its complementary events. So we need to show the probability the complementary events is x equal to 0, s is non-negative integer value. This guy goes to 0. Okay, this is our goal. All right. Now we use Chebyshev. How do we use that? Okay, let me first state the theorem. To prove a random variable having value 0. Okay. For this, do we need x to be? Don't think so. Let me first state the theorem. The probability that x equals to 0 is at most the variance of x divided by expectation square. Okay. So in particular, if the variance of x is much less than the expectation square, this guy goes to 0, and we have what we need, right? Then probability x goes to 0 is 0 tends to 0. Okay. Do we need any restriction on x? Probably not. Let's see the proof. And from proof, we will see if we need anything. What does it mean x equal to 0? The probability, these events, remember, if an event A implies event B, then the probability of the event A is at most probability of event B, right? So what does x equal to 0 implies? That implies that x deviate away from its expectation by more than its expectation, right? Is that correct? Right. Okay. So then by Markov, and let me remind you what's that's not Markov, Chebyshev. Then by Chebyshev, then Chebyshev, where we're going to take k equals to, we want k sigma to be mu, right? So k is mu over sigma. We have this probability is at most 1 over k squared, which is sigma square over mu square. And that's exactly what we want. Sigma square is the variance. Mu square is the expectation square. Good. Easy. So coming back here. Now we need to show for any p much larger than 1 over n, the probability that the number of triangle goes equals to 0 goes to 0, right? This probability, which is, by this theorem, it's enough to show that the variance of the number of triangles is much smaller than expectation square. So that means we need to show for the threshold, we need to show the variance of x is much smaller than the expectation square. And recall, expectation square up to is roughly up to a constant factor. Expectation is what? N cubed p cubed over 6. Forget about over 6. Up to constant is N6p6. Okay? Up to constant. So we need to show when p is much larger than 1 over n, we have this inequality. Let's compute what's the variance of x. Okay. So the variance of x, how do we compute it? Okay. Recall, x is the sum of xa, where a is a triple set of vertices. And this is the indicator function that A induces a triangle. So the variance of x, as I mentioned, equals to the sum of variance of xi. I goes from, oh sorry, A. Plus the covariance, plus the sum of A not equal to B, the covariance of XA and XB. Okay? Remember, this is, I just expand the variance like this. Okay? No problem. Now, we need to show each one of these term is much smaller than n to the 6, p to the 6. So let's first look at the first term. For the first term, this is second term. For the first term, let's first look at what's variance of XA. Variance of XA equals to the expectation, by definition, XA squared minus the expectation of XA squared. But this is an indicator variable. It's a 0, 1 valued, right? This is 0, 1 valued. That means this thing is the same, it's just itself. XA equal to XA squared. Oops. And then this equals to the expectation itself. This is non-negative. Let's just drop it. So this is at most the expectation of XA. No problem. So we have, this implies that the first term, which is the sum over all variance of XA, is at most sum over expectation of XA, both ranging over all A. This is nothing. Linearity of expectation is expectation of X. Okay. And what do we know? We know at this range of P, expectation of X, N Q, P Q tends to infinity. So this quantity tending to infinity, of course, is a lower order term for a quantity that's square of that. So this is much less than EX squared if P is much larger than. Okay, so the first term, no problem. Let's look at the second term. Second term is the covariance. So the covariance, remember, covariance of two random variables is 0 if they are independent. So when are A and B independent? So for 2, X A X B independent if A and B, they don't share any pair of vertices, right? So if A is like this, if A is like this, and B is like this, or AB is like this is A, this is B, whether this form a triangle has nothing to do with this. Whether this form a triangle has nothing to do with this, because we put an edge for every pair independent of all other pairs, right? And that means when A intercept B is at most 1, we don't need to consider this. We only sum over all AB where their intersection is exactly 2. A equal to B equal to 3 intersection, then they are the same sets, right? So it's exactly equal to 2. So AB dependent when equal to 2. So we have the second term equals to the sum of all AB equals to 2. The covariance of XA, XB. Oops, what did I do? And this is sum of AB equals to 2. What's covariance? It's the expectation of XA, XB minus expectation of XA, expectation of XB. Okay. Good. Now, XA is indicator function, not negative. This is not negative. This whole thing is not negative. We can drop it to upper bound it. So this is at most. So 2 is at most sum of A intercept B equals to 2. Expectation of XA, XB. So far, so good. All right. We need to show that this term on the right is much smaller than expectation square n to the 6 p to the 6. So let's draw some picture. A, B share a, so if this is A and this is B, right? Let's say this is B. This means both A and the expectation of this is the probability that both A and B induce a triangle. That means all these 5 edges needs to be there. 1, 2, 3, 4, 5. Okay, so this equals to sum of A intercept B is 2 p to the 5. So we just need to upper bound the number of pair of triple sets intersecting at 2. This is at most what? Well, it's trivially n to the 4, basically, but there are some different roles to play for intersection of AB. So you first choose 2 vertices for intersection of AB. Now you choose in the remaining one vertex lying in A, one vertex lying in B, times p to the 5, right? This is roughly n to the 4 p to the 5, which easy to see. It's much smaller than n to the 6 p to the 6. We are done. Any question? Okay. Second moment. So we've seen one way of applying second moment to prove one side of a threshold phenomenon, the Chebyshev inequality, and this inequality is very important. Let me highlight it. If you want to prove some random variable, if you want to prove that the random variable some random variable x is very likely to have a positive value. So the probability that x, some random variable x, being 0, you want to prove that this is unlikely. It's enough to show the variance of x is much smaller than the expectation square. Okay. So using this, we proved one side of the threshold phenomenon. So you see this second moment Chebyshev and also this Chernoff type we've seen, concentration measure, you can all derive it from Markov's. Markov is very useful. Another very important application of second moment, sometimes second moment is already strong enough to control the analysis of some random algorithm. And then one very important example, classical example, is this method called Riddle nibble. So the philosophy here is that we want to prove certain nice structure exists. So the philosophy, the idea here, is that we would like to show, some desired structure exists. And we don't know how to construct this structure explicitly. Okay, so we would like to do it randomly, and we would like to construct it randomly, and would like to prove this by random construction. Wait. Okay. Now the problem is, if we construct this structure, if we take some random structure all at once, then there's too much randomness, too much dependency, and it's very hard to analyze. So if we take, if we randomly construct things all at once, there's too much randomness or dependency that we can handle. Dependency to handle. Okay, so this is, we cannot prove that the property that we want for this structure holds. So instead, what we do is we don't construct this whole thing, the building, all at once. We construct it floor by floor, right? You first construct the basement, then first floor, second floor, third floor, and the 100th floor if you build a skyscraper. So we're gonna take a small, this is where the name comes from. When you eat a bowl of rice, you don't just chuck the whole bowl of rice. Oh, you don't eat one grain of rice at once. You're gonna use chopstick to pick up a bite that's good enough to fit in, right? So we're gonna take a bite. Nibble means a bite, a small bite at once. And this small bite of randomness is just small enough we can handle the dependency there. We can analyze how things change after each bite. And then we're gonna do multi-round of bites to finish this bowl of rice. Okay, so to take instead, we take a small bite each time and do multiple rounds to finish it. Okay, let's see example. This is still very philosophical. What do I mean here? So historically, perhaps the most classical example, this is where Rödl initially come up with this Rödl nibble idea, is when he resolved. So historically, Rödl has resolved a conjecture of Erdős and Hanani. This conjecture is about asymptotic optimal packing coverings of sets. Okay, some design related thing. This can be phrased in terms of finding almost perfect matchings in hypergraphs. So this is the theorem. Later, simplified version, the proof is given by, initially proved by Rödl. So later proved by Pippinger and Spencer. Pippinger and Spencer. This is very famous, very, very useful results. It says that for a hypergraph, if it's almost regular and the co-degree is very small compared to the degree of every vertex, then one can find an almost perfect matching. For any R-uniform hypergraph, if we satisfy these two conditions, first, it's almost regular. This means that the degree of every vertex is 1 plus little o1 times d for any vertex v. And the co-degree is small. Co-degree small means the number of edges containing any two pair of vertices is little o of d for any uv pair of vertices. Then, if we have these two conditions, there we can find an almost perfect matching. That means a matching of size 1 minus little o1 times n over r. So this is n vertex, of course. Okay. Any question about the statement? All right, so this is the most classical example to explain Rödl nibble. Since this is very detailed explained in Alon Spencer's book. I will not prove this example. I'll just tell you the idea. And instead, I'll illustrate a different example of this Rödel nibble type argument. So let me first tell you the idea for this one. So idea for Rödel Pippinger Spencer is we're gonna, as I said, if you do everything all at once, it's very hard to do that. So namely, if you choose a set of n over r edges, very unlikely, or at least it's very hard to say why this random set of n over r edges contains almost perfect matching. Instead, we take a small 1% of the vertices. We take 1% of n over r edges. So n over r times some small constant of edges. And we will show that in this small set of edges, very few vertices are covered more than one by more than one edge. So you just delete these vertices that cover by more than one, right? So we show that if you take a small set of edges, a small epsilon n over r set of edges, then only tiny vertices are covered more than once. You delete these vertices, then the remaining edge will form a matching, covering almost all vertices spanned by this set of edges. Okay, so fix a small epsilon bigger than 0. We're gonna take a random set of epsilon n over r edges. Let's say this is edges, let's call it E1. This is epsilon n r edges, E1. And we can show that this random epsilon n over r edges has an almost matching. Has an almost perfect matching, covering at least epsilon n minus epsilon square n some vertices. Okay, just a tiny bit. When epsilon is small, this is lower order term. Just a tiny bit vertices, it's not covered. Yes, maybe I should say contain. Okay, now what we do is we delete this E1 and then look at the remaining graph. Then repeat. What's important is so E1 has these two properties. The first property is that E1 contains an almost perfect matching covering almost all vertices. The second property is that the remaining hypergraph, so H with the vertices in E1 removed, still satisfy this sort of pseudo-randomness property. Still satisfies this property. Well, of course, with a different, this little o parameter. Okay, so one has to be careful. Then we can iterate. Take another set E2 of these many edges. We can cover almost all there. Repeat. Okay, you iterate about I believe you iterate 1 over epsilon log 1 over epsilon rounds. Okay, but anyway, iterate whenever there are at least epsilon n vertices left. Whenever you have more than epsilon n, you can do that. And that's it. Okay. This is the idea. Look, this many rounds, if at the end there are less than epsilon n vertices left, you just throw them away. Our goal is to find almost perfect matching. You don't care about this negligible amount of vertices. And because you have this many rounds, each round you lose epsilon squared times n. Still, the leftover vertices is like this. When epsilon goes to 0, this is little o n. Okay. That's all I want to say. And second moment can be used to analyze these. You don't need any higher moment. Okay. So second moment can be used to obtain this iterative round. This is all I want to say. Any question? Okay. Now, another example, I would say also classical, of this flavor, Rödel nipple, is, let's look at this example instead. Finding independent sets in triangle-free graph. So this is by Turan's theorem. So now let's look at independent sets. In triangle-free graphs. By Turan's theorem, it's easy to show. You can rephrase Turan's theorem to show that for every graph G, n vertex graph G with average degree, d of G is T, D, then you can find the independent set of size n over d plus 1. If you haven't seen this statement before, prove it. Okay, I'll leave it as exercise. So we can find the independent set of size roughly n over d. Okay. This is optimal. We cannot improve it. For example, G can be union of KD plus 1, right? If you union of KD plus 1, for independent set, you can only pick one vertex from each clique. So you get exactly n over d plus 1. But this has large clique. If you don't have large clique, can you improve this? This is what I-type Comlish and Samarity established in the 80s. And this is the theorem we will see a proof of, their original proof. So this is I-type Comlish and Samarity 81 maybe. So they use this result to construct some infinite sit-on sets for some number theory problem. They prove that for any n vertex graph G with average, which is triangle free, and average degree D, then we can improve this Turan bound by a log in D vector. Then the independence number is at least, let's say 1 over 1000. They can prove 1 over 100 maybe. I don't really care about constant. Times n times log D over D. Okay. This is the extra term. Compared to above. Okay. So let me first say their key lemma, which is the nipple step. Any question about the statement? So if we want to prove this randomly, how do we prove it? We prove that A naive way would be we choose a random set of n log d over d vertices, a random set, and prove that it's independent. But as I said, you cannot eat the watermelon all at once. It's too big. So instead, we're going to find independent set of size n over d in each bite, in each nibble. And then we're going to repeat these log d steps. All together, we put these independent sets together, we get a large independent set of size n log d over d. So here's the key nibble step. The key lemma, which is the nibble step. In each bite, okay, let me write down what's this nibble step. For any n vertex graph G with average degree equals to t, average degree equals to t, which is at most, let's say n over 100, not too dense. Then there is this subgraph K of G. There is this subgraph such that the following holds. What? Well, first of all, K has exactly n over 100 t vertices, okay? And the number of edges in K is very small, very sparse. V of K over 50. Well, what does this imply? Remember, by two-round theorem, we can find the independent set of size at least number of vertices over average degree. Here, average degree is smaller than 1, right? So you can find an independent set of size, number of vertices over average degree plus 1, so over 2. You can find in K, there's the independent set of size n over 200t. No problem. Half of vertices, okay? So this is the each byte, right? In each byte, we're going to take an independent set. But after you take this independent set, we want to find another independent set in the remaining to put it together to do it multi-rounds. To do that, look, this is K, right? Then we need to throw away the neighborhood, the vertices that has neighbors in K. In the remaining, we call this remaining graph M. So M is the graph G with K and its neighborhood removed. Okay? Then here, if you have an independent set, then together with the independent set here, there's no edge in between. It's okay. No edge in between, right? M satisfy what? M satisfy also two property. M has at least n over 2 vertices. So at least half of the vertices remained. And what do we do in M? We want to find independent sets. And the only way we know to find independent sets is taking this naive one, n over the average degree t. So we want to make sure that in this graph, the relative ratio of n over t is not dropping too much. So this is written as n prime over t prime, where n prime is the number of vertices of M, and t prime is the average degree of M, okay, is at least some theta of n over t, where theta equals to this thing. So this is the key verbal step. Any question? Now what we're gonna do, all right? So we start with a triangle-free graph with average degree d. We want t. We want to prove you can find the independent set of size up to some constant n log t over t. We do this nibble step. We take a bite from the bowl of rice. We take this set k, subgraph k, so that inside k, we can find the independent set of size n over t. And then we know in the remaining, if you delete the neighborhood, in the remaining, we still have half of the vertices left. You repeat. You take another k, take an independent set of size n over t inside, delete its neighbor. In the remaining, we still have half of the vertices left. So n over 4 vertices left. Repeat. Log d step. So altogether, we have this independent set. So let's first see how we can derive this theorem from this nibble step. All right? And next time, we will see how we prove this nibble step. So let's first derive the main theorem. Prove lemma implies theorem. First thing to notice is that we may assume the average degree of the triangle-free graph is at least, may assume. So if our average degree is, let me just write t maybe. To be consistent. So if average degree t is more than square root n log n, then what? Well, this is a triangle-free graph. If average degree is more than this number, well, the neighborhood of any vertex is independent set by triangle freeness. We will get the independence number is at least the maximum degree or the average degree, which is at least n log n. But n log n is bigger than, not n log n. I want to use, now t is bigger than n log t over t. Okay? Why? Move t to the other side. So t squared is smaller than this. It's the same as t is larger than square root of that, n log n. Okay, that means we may assume t is smaller than n log n. All right. Now we have a triangle-free graph with minimum degree, with average degree smaller than square root n log n. Let's first apply the nibble step. By nibble step, inside this k, we can find the independent set of size n over 200t. So by nibble step, we find I1 inside an independent set of size n over 200t inside, let's say K1, the first application of, and we have M1 is what? G minus VK1 union, the neighborhood of that, right? Good. And what do we know? We know by the lemma, VM1 has at least half of the vertices. And we know that N1, which is order of V1, this is N1, okay, over D1, so D1 is the average degree of M1, is at least theta 1 n over D, where theta 1 is 1 minus 1 over T. Oh, I use T. Oops. Minus 10,000 T over N. But what do we know about T? We know T is less than this, right? So this is actually larger than 1 minus T to the negative 1/3, as T is smaller than N log N. No problem. So we have this. Now, we're going to repeat. Use lemma in M1. For each I, use lemma in Mi. So in M1, we're going to find K2. So you find Ki plus 1, Mi plus 1 with this property. Okay? So let's do some computation. Case 1, suppose we're going to define Ni, Ti, theta I in similar way. Okay? Suppose case 1 is we can go on this iteration for many steps. We can go on for capital R equals to 1/2 log T many steps, and always have, suppose we always have theta, for each theta I is at least 1 minus 1 over log T. Okay? Then we are done, because let's look at the final step. For each step, for each I and most R, we can extract in Ki an independent set of roughly this size, right? Ki contains up to a factor of 2, at least Ni over Ti, which is at least theta I. Is this theta I? Yes, this index is the same. Theta I times ni minus 1, the previous step. So this equals to theta I minus 1, previous step. Dot, dot, dot. You have the product of theta j goes from 1 to n, to I. The last step is just n over t, right? The original thing. But what do we know? We know that we carry out this many steps. Each step theta I is large. So this is at least 1 minus 1 over log t. Carry out capital N, capital R steps. Capital R, I is at most R, so it's 1/2 log t times n over t. What is this? 1 minus epsilon to the power r is roughly e to the negative epsilon r. So this is roughly e to the negative log t, 1/2 log t. So this basically cancel out. Negative 1/2 times n over t is bigger than n over 10t probably. Okay, so at every step, every one of these ki will contain the independent set of the size we want, n over t. And we carry out this many steps. We are done putting together. Case 2. Suppose we cannot go for this many steps. And at some point, this drops. Theta I drops too much. So at some step r strictly less than 1/2 log t, this is this capital R, right? We have theta r drop too much, less than this. What this means actually is that the graph MR is too sparse. What it means is MR too sparse. This already implies MR has a large independent set, and we are done. To see this, let's do some calculation. Theta R, if it's smaller than this, we know that it's bigger than 1 minus TR negative 1/3. Okay, for every theta, we have this. This might be, if this is R, this is R minus 1 maybe? Let me see. Okay, yes. Check. Okay, this implies that TR minus 1 is at most log T cube. Okay. What that means is that just look at, this is the graph MR minus 1. So alpha of this is at least NR minus 1 over up to a constant 2, TR minus 1. This is at least, remember, N every time drop by a factor of 2. And TR is at most, so you put log T cube. Okay. What do we know about 2 to the R? By this, 2 to the R is smaller than square root T. Okay. So this is at least N over square root T log T cube. When T is sufficiently large, this is definitely bigger than what we want. And we are done. I go over a little bit. All right. This concludes today's lecture. So I show you how to iterate this nibble step, log T steps to get the independent set that we want. Here's all the calculation. So next time we will see how we can use the second moment, the variance, to achieve this nibble step. Any question? Okay, if there's no question, I will see you guys on Thursday.